We're very excited now to have one of our sponsor talks. Ramin, who is the CEO over at Eliyan, is here. First off, thank you so much for being a sponsor, right? Being able to host conferences like this depends upon people being willing to sponsor, and we truly do appreciate your support for that. Ramin is the inventor of over 130 granted patents or pending patents in communications and networking. Has just a fantastic background. Great track record of creating differentiated connectivity technologies that's been adopted by the industry as standards, 2 Ethernet standards at the IEEE and 1 chiplet connectivity at OCP. He has co-founded Velio Communications, which was acquired by Ramba/LSI, and then at Aquantia, which went public and then was acquired by Marvell. He has a PhD from Stanford, and his current the current endeavor at Eliyan is around multi-die chiplet interconnects. And as the new processors have all come out, multi-die becomes ever more important. The die-to-die interconnect becomes more important, and of course optimized for high bandwidth, low latency, and low power. So definitely a technology of keen interest to many in the space, and thank you for being a sponsor, and it's all yours, Ramin.
Thank you very much, Alan. So let me try sharing. Hopefully you'll see my slides. All good?
Looks great.
Perfect. So good morning, everyone. In this talk, I'd like to talk about Universal Memory Interconnect, or UMI, is a solution that we propose to the industry, and basically derivations of that as well, as a practical solution to solve the challenges, the bottleneck of AI systems and AI ASICs, especially the memory wall, in a practical way. I mean, you've heard about some of the recent challenges in packaging of these large GPUs, and this is our proposal as a way to address these challenges. So, of course, chiplets have been around for a few years now. Everybody is familiar with them. They give us reduces the development time and cost, reduces the overall cost of systems, faster time to market. You don't need to develop every piece in every new process technology. You can mix and match these chiplets together. Smaller form factor, and most importantly, and say one of the dominant reasons that AI chips are using is because of the heterogeneous integration of putting different chiplets that are optimized in their own process together and build a large system inside the package and connect them together at very high bandwidth with high power efficiency to be able to deliver such high performance. And that's why you see that all AI chips, GPUs, TPUs, and so forth, are leveraging heterogeneous integration of chiplets one way or another. And that's becoming more and more dominant. And in fact, as the demand for AI never stops, this insatiable demand of higher performance, low power, the push is to put more and more chiplets inside these substrates and create these heterogeneous integrations of, let's say, sub nanometer or nanometer type processors in 2-3 nanometers, together with DRAM processors, all integrated on the same package, as well as the optical solutions and in form of CPO, all inside one package. And that provides significant higher performance, but of course, at the same time, will drive the size of the substrates to put together these chiplets and integrate these chiplets together really large. I mean, what we hear from industry is that the next generation of these chips are targeting 10 reticle, which is, I would say, roughly 8,000 to 10,000 millimeter squares of these substrates that they all need to be connected together, which is a huge challenge. Of course, silicon interposer, such as CoWoS, has been the main vehicle to interconnect these chiplets together as an advanced packaging. It provides high density of wire, fine bumpages on the chiplets that you can run really high bandwidth between chiplets at a low power. And that has been the de facto standard for interconnecting chiplets, has been in production for a while. And of course, because of these high density of wires, you can get large bandwidth, which is defined in form of terabits per millimeter for chiplets, meaning on each edge of a certain ASIC, how many terabits you can get per millimeter. And silicon interposer can give you at least 5, going to 7 and 10 and beyond terabits per millimeter, which is a big advantage, of course. And also, all these interconnects are done by a single mask, or maybe a single set of masks. So all connections, all bumps, or everything all self-aligned because they all come from a single set of masks rather than having separate masks inside the substrate and try to align these separate masks together. And the substrate is also silicon, so its thermal coefficients of expansion is same as the chip that we put on them. So there's no warpage issues and so forth. But of course, there's a size limitation. And that's why people beyond, let's say, 2.5x reticle, before going to 3x reticle, are moving away and are looking into alternative approaches. And this is mainly because, if you want to use a single mask to connect all these things together, there would be a limitation of the size of the mask that you can have. So people have moved to alternative solutions. So rather than having one big substrates all from the same mask, using separate bridges, silicon bridges, still with high density between these different chiplets. And this is a great thing. We call it CovaCell or EMIB. Of course, less expensive because the main material is mold. But and the size can be bigger because it's not limited by the size of the lithography mask. And the issue is that the alignment of these chiplets can be far away from each other. Maybe the center one can be as a reference, but if you want to put another one which are tens of millimeters away from the center one, there will be certain alignment mismatch within micrometers that can lead into problem. Another big issue is, of course, the material used here can have different coefficient of the expansion, which is typically what we hear is about 4x that of silicon. And that can cause major warpage issue. This is shows a high-level view of what we're talking about, that the center one can be used as a reference, and this is what is necessary to provide high bandwidth between these ASICs. But as you go farther, tens of millimeters away, there is a mismatch. Even tens of microns of mismatch between these will create a weak connection. Now imagine because of thermal issues, this whole substrate expands and this weak connection will break because of warpages. So the question is, can we, while we have to live with these silicon bridge in the middle, can we avoid having silicon bridges on the periphery, on the edges when connecting to these HBM? The good thing is the bandwidth that we need going through HBM or anything that is periphery is not as high as what we get in the middle. And this is where our proposal comes in, that what if we can live with a standard package, a standard organic package kind of bandwidth that, or type of density of wires and bumps to provide this bandwidth. This provides a very high-level view of different technologies for die-to-die, whether it's fixed unidirectional UCIe or configurable bidirectional. I just want to focus the attention on these two, which are dynamic or simultaneous bidirectional, which you use a single wire or single pad or bump to transmit or receive. That by itself will give you 2x advantage in the number of wires or bumps that you need, which, of course, advanced packaging give you high density, but by leveraging this, you can reduce the density by a factor of 2 effectively. And that's a step direction into using less advanced, less dense, less type of advanced packaging for these interconnects. Our focus are on in both of these guys, but especially for memory, dynamic bidirectional is a simpler solution because you can either transmit or receive. At the same time, you don't need to have echo cancellation to simultaneous manage your transmit signal that you put on the same line that you're receiving. And this is also very beneficial for memories that you only read or write. And this is what we have proposed into both OCP and JEDEC as well. At OCP, it's called like both 2.1, or we call it UMI. And we've also proposed a version of that at JEDEC called, we call it SPHBM, or Standard Package HBM, that effectively by leveraging this technique, if you need, let's say, N wires to transmit or N wires to receive, you can go to total of N wires rather than 2N to transmit or receive. And so this is one step direction to reduce the density of wires that you need. And of course, you want to go even higher bandwidth rather than staying with low bandwidth of typically HBM is 6 to 8 gig. If you want to go even to higher bandwidth of 32 gig, that provides another advantage of reducing the wires. And of course, these technologies have been done and implemented. We've been working on it since 2017 and 18. But especially the latest chip that we have in 3 nanometer, which we go 32 gig in each direction, effectively give you 64 gig per wire. It gives you 5 terabits per millimeter on a standard package, but even all the way up to 20 terabits per millimeter on advanced package. And here are just some internal eye diagrams of the chip that we have in silicon in the lab, and the next generation is coming up next month. But of course, you can build these solutions, high performance links of 32 gig on advanced FinFETs. HBM historically had been using just standard DRAM process, which is super slow. And we have been pushing and talking to industry to switch the base die of this solution, of especially HBM, to have FinFET because of all the advantages that it offers to the industry and to especially the AI chips. And eventually, Samsung was the first to adopt, SK Hynix and Micron followed, to change the base die of the HBM to FinFET. And once the FinFET base die is there, we can build high performance die-to-die chip, die-to-die PHYs, which goes up to 32 gig, even beyond, with also the logic to manage this dynamic bidirectionality, and therefore enable running over standard substrate. Just imagine this lane going 8 gig versus 32 gig, and you leverage the factor of 2 of UMI. You're talking about factor of 8 effectively reduction in density that you can implement the whole thing on standard package as a result for connection to HBM. And why is it good? For example, in the case of Blackwell, you need a 3.5x reticle potentially to put all the 8 HBMs and 2 compute ASICs. But if we use the UMI or SPHBM effectively, you only need a 2 reticle chip to connect these 2 compute ASICs at these high bandwidths together, and put the rest of the chip HBMs off package. 2x reticle has been proven to be super high volume, good yield. And in addition, of course, you can still leverage the bidirectional, simultaneous bidirectional link on a standard package just showed you to provide even high bandwidth between these 2 groups. So we can have an even larger solution with 4 ASICs or the processors and 8 HBMs, even all the way up to HBM4 inside a single package, leveraging these techniques. So in summary, everybody knows that chiplet-based SiPs will provide significant advantage for high-performance AI, and that advanced packaging, silicon interposer, silicon bridges are really necessary to provide high bandwidth between these compute ASICs. And specifically, silicon bridges are needed to go beyond certain size, but the mismatch alignment between pad and bumps and, of course, the thermal expansion has caused some yield issues that we try to address that with a different approach using standard packaging, with the standard packaging PHYs on the periphery, on the edges, such as UMI or SPHBM, to remove the need of silicon bridges on those periphery. And as a result, provides high performance, even higher performance than what we can get existing on these silicon bridge type interposer, and with high yield as a result of this solution. Thank you. Any questions?
Outstanding. Thank you so much, Ramin. That was really quite good.
Well, you're welcome.
So there is there's a channel that's available for questions on Slack. All right. So please be sure, if you have questions for Ramin, please be sure to add it into Slack.
Great. Thank you, Alan.
Thank you so much.
Yep.